Hi, everybody. Thanks for having me. So this is my first time coming to the Ad Filtering Dev Summit, virtually or physically. So when Cornelius invited me to come and speak, I asked him to tell me a little bit more about what the Ad Filtering Dev Summit's about. So what he told me was that this is a place for everyone who wants to enable users to have empowering and positive online experiences while enabling other stakeholders to monetize their content. And that got me excited because I resonate with that vision quite a bit. And then he said that from eyeo's perspective, one of the biggest questions for the future of a healthy internet is how we're going to develop and implement new measurement use cases that don't require tracking. And that clinched it for me. And then I was like, okay, yes, I'd be happy to come and talk because that's exactly what I work on. For the last few years, this is what I've been pursuing. Fortunately, I'm not the only one doing so. The Private Advertising Technology Community Group, or the PATCG, we founded about a year ago. Mozilla was the one that really got together and said, hey, we don't have a place that's the right place to talk about advertising topics in the W3C. And under their guidance, we formed this community group, and we're forming a working group. There's over 300 members that represent everybody from users like the Center for Democracy and Technology, or browser vendors, ad tech vendors, publisher groups, advertiser groups, the like. And right now we have exactly one work item that we're working on, trying to do just one thing, and that's private measurement. So you can see here our GitHub page, a little bit about what this is, but what is private measurement exactly? What do we mean by this? So I'll try to describe what the goal is. So if you zoom out 10,000 feet, if you're an advertiser and you spend $1,000 on ads, what you want to know is, what did you get? So if those ads led to like 273 purchases on your website, that's what you want to know. You want to know that number, 273. And this sort of result that you want is an aggregate result. What do I mean by that? What I mean is that it's not linkable to specific individuals. We want a system where this number that you get out, we can't tell for an individual if they're a part of that count or they're not a part of that count. And more than that, if you're this business who's getting this result, we want to design a system where at no point along the way was that business ever even exposed to the private user data, like their browsing history. They don't need to see that in order to compute this count. And if there's some operator or operators that are operating this private measurement system, we want them to be minimally trusted. We'd like to design a system that pushes down those trust requirements on that operator as low as possible. So to be concrete about what I mean is, from the business's perspective, I don't want to have to trust that operator with confidential business data. Ideally, they're never even exposed to my confidential business data. And if I'm a user browsing the web and seeing ads, I never want that operator to ever be exposed to my private user data, like my browsing history. So that's a tall order, but that's what we're trying to do. But it gets even more complicated when we say, well, assuming that there is some operator of this system, what if they get curious and they decide to spy on somebody? Or if they're compromised by a hacker who invades their system and gets access to their servers? Or if they're compelled by some government to hand over all the data on their servers? Even in those cases, we want it to be the case that no private user data is ever exposed. So there are 3 proposals on the table for how we could possibly go about creating such a system. Google Chrome put forward the Aggregated Reporting API proposal. Apple WebKit put forward the private click measurement proposal. And most recently, Mozilla and Meta teamed up to put on a 3rd option on the table, interoperable private attribution, or IPA. So I'm one of the authors of this proposal, and this is the one I'm here to talk about mostly. But I think in reality, we're unlikely to ship any of these 3. More likely than not, we're going to ship some new standard that steals all the best ideas from all of these things into some new hodgepodge that is like better than all the sum of its parts. But for the moment, I'm going to talk to you about some of the big ideas in IPA. So before I get into IPA, I'm going to cover 3 big ideas from academia that we've been inspired by and that feature in IPA. And then once I've covered that, I'm going to go into how IPA works. And my hope here is to sort of demystify this a little bit, because sometimes multi-party computation sort of sounds like magic, and it's not. There's nothing magical about it. So my goal is that anyone who's taken algebra can understand and say, oh yeah, I get that. That makes sense. And there's nothing magical about this. Okay, so the first big idea from academia is this concept called secret sharing. So if you have a secret number, like this number here, my Facebook user ID is 205,404. What you can do to secret share it is generate 3 random numbers where if you add them up and you just look at the last 6 digits, it's the secret number. Okay, now there's like a nearly infinite number of ways of secret sharing this number. You could use these 3 numbers, you could use these 3 numbers. It doesn't really matter as long as the last 6 digits of the sum add up to your secret number. And all that's important is that these numbers are all randomly distributed equally and evenly around the entire 6-digit range, and that they add up correctly. So the thing I've just described is called additive secret sharing. And the cool thing about secret sharing is if you've got just one of these 3 pieces, what can you learn about the secret number itself? Well, nothing. You can't narrow it down at all. If you only have one of these pieces and you don't know what the other 2 are, the secret value from your perspective could be any 6-digit number. And every one of them is equally likely. So you can't like narrow down the range at all. What happens if you have 2? Well, you still learn nothing. If you have 2 of these 3 pieces, as long as you don't know what this 3rd piece is, the secret could be any 6-digit number, and they're all equally likely. So remember that we're trying to design a system where if there's an operator or operators running this system, they're minimally trusted. So in our IPA proposal, what we have proposed is that there are 3 helper parties working together to run a multi-party computation. And since they're all minimally trusted, we give each one of them just one secret share. So on their own, none of these parties can learn anything about the secret data that's coming in. So for each of these users, they have some private information that they don't want exposed to the system. They secret share it before sending it to the helper parties. Same thing for business confidential data. So from each helper's perspective, they've got one of those shares. And like we just discussed, from that, they can learn absolutely nothing. Now, earlier, I alluded to this idea of what if you have 2 of the 3 pieces and said you still learn nothing? Well, that's another kind of secret sharing. It's called replicated secret sharing. And it works like this. Helper 1 would get piece 1 and 2. Helper 2 gets pieces 2 and 3, and helper 3 gets pieces 3 and 1. And again, like we discussed, they can't narrow it down at all. They have no information whatsoever about what the secret is on their own. But this is a cool secret sharing that helps us do some things efficiently later on. So this provides what we call input privacy. It satisfies that constraint of ours where the helpers individually are never even exposed to any private user data. They just see secret shares. And they're never even exposed to your confidential business data either. They just get secret shares of that as well. Okay, so the second big idea from academia is that you can do math on secret shared numbers. This kind of blew my mind when I learned about it. I think it's kind of magical. So first, some notation. If I'm just writing a number, I'm going to write it like this A here. But if I'm talking about a secret sharing of a number, I'm going to put brackets around it. In all the sort of academic papers that I read about this topic, this is usually the notation that they use to describe a secret sharing. Okay, so you can devise an addition protocol where if you have a group of 3 helper parties working together, if each of them has a secret share of A and each of them has a secret share of B, they can compute a secret sharing of A plus B. And the cool thing about this is none of them ever knew what A was or B was or what A plus B is, but somehow they can do this. So this is actually it's pretty straightforward to explain how it works. Okay, let's put on our algebra class hats here. So again, if you have A defined as A1 plus A2 plus A3, so these 3 things added together, and same for B, then what's A plus B? Well, it's just all those things added together. And if you just kind of rearrange the terms a little bit and put the 1s together and the 2s together and the 3s together, what you see is that, well, helper 1 has all the information necessary to compute this green bit. It's got all the 1s. Helper 2 can compute this yellow bit because it's got all the 2s, and helper 3 can compute this blue bit because it's got all the 3s. So by just taking its secret shares of A and B and locally adding them, they've somehow computed a secret sharing of A plus B, with none of them ever learning anything about A, B, or A plus B. So that's pretty cool. But the really cool thing is the multiplication. You can actually multiply two secret shared numbers. And again, they never learn what A, B, or A times B is. This one, again, just algebra, nothing particularly complicated. But we're going to use replicated secret sharing this time. So just a quick reminder, in replicated secret sharing, they've each got two pieces. Well, if A and B are defined as before, then what's A times B? Well, it's just that first thing times that second thing. And if you do all that distribution out, you'll see there's 9 terms. And if you group them around again and put all the terms with 1 and 2s here, and terms with 2s and 3s here, and all the terms with 3s and 1s here, you realize helper 1 has all the information necessary to compute the green part. Helper 2 can compute the yellow part, and helper 3 can compute the blue part. So with the information they have available, they can compute an additive secret sharing of A times B. That is pretty cool. Now, there's a little bit more to this where how do you get back to a replicated secret sharing? And I only have a 25-minute slot, so I can't go into all the details. But this is the basic gist of it. OK, so once you have addition and multiplication available, you can do a lot with that. So if you have a whole bunch of secret values, perhaps coming from a lot of different users, they can all get secret shared. And then you can just combine a whole bunch of multiplication and addition things and sort of daisy chain them together and make some big web of operations to go compute some function. And the cool thing is all the inputs remain private from the helpers. They never get to learn what any of the inputs were that they're operating on. All the intermediate values are also still secret sharings, and they'll learn nothing about them. And if you want, even the outputs can remain private, where the helpers only have a secret sharing of the output, and they give you, the consumer, all 3 secret shares, and you add them back together to get the output. So what's cool about this is if you get really clever with how you secret share the input original data and make some complicated string of additions and multiplications, you can compute any function in MPC, where the helpers never learn anything about the secret shared data coming in or out. So what we've done with IPA is we designed a private measurement system that can be executed in MPC. Okay, so this takes us to the third and last big idea that we've taken from academia, which is security models. So again, we're trying to design the system where we place as little trust in the operators of these MPC helper nodes as possible. So it's worth discussing what happens if one of them gets compromised. And we'll take the Apple's 3 Cs thing, like what if they get curious, compromised, or compelled? So let's imagine a hacker breaks into their data center and has access to everything on their servers. What do you learn? Well, there's 2 different security models that people talk about in academia. One is called honest but curious. In that model, user privacy is preserved so long as all the helpers just stick to the protocol. If they just stick to the protocol, they can learn no private information, even if they got, really curious and recorded everything that they saw flying past them and kept track of all the secret shares. That's great, but we're holding IPA to an even higher bar than that. We want what's called malicious security with abort. So with that, even if one of the helpers deviates from the protocol in any arbitrary way and attacks the thing, it can still learn no private user information. And what's even better is that helper parties 2 and 3 here, in this case, the other remaining honest helpers, can detect that something has gone wrong, that somehow the protocol isn't working correctly, and they can just abort. And the thing produces no output whatsoever. And they can probably figure out whose fault it was and kick them out of this multi-party computation network in the future. So malicious security with abort is really hard. It's a high bar, but we've managed to achieve it with IPA. Okay, so now that we've covered these 3 ideas from academia, I'm going to give you this broad brush strokes of some of the basics of IPA. We don't have time to go into all the details, but hopefully you walk away with a high-level understanding of how it works. Okay, we've proposed adding basically one really important API to the web platform. And when I say the web platform, I mean web browsers and mobile operating systems like iOS and Android. And this function would be called something like get encrypted match key. So we're envisioning a world where browsers and mobile phones have some concept of a user ID, kind of like an IDFA. Like it's a unique number that exists on your phone. But unlike the IDFA, it would be kept private. No app would ever have access to this. Or if we're talking about a browser, no website would ever be able to access this number. Instead, you would call this get encrypted match key function. And when you do so, the browser or the mobile operating system would take the match key. It would randomly secret share it. So I've done it here, made these 3 random looking numbers that when you add them all up, give the match key. And then it would take each of the 3 pieces and encrypt them towards one of the 3 helper nodes. And if you as a web developer or a mobile app developer call this function again on another app or a different website, it's fine. The browser or the mobile operating system will just generate a new random secret sharing of the match key and encrypt the 3 pieces towards the same 3 helper nodes. So the really cool thing about this is that it means that it's unlinkable. So even if the same visitor visits website 1 and website 2, and if website 1 and 2 both call this get encrypted match key for all the visitors to their website, even if this sort of first row corresponds to the same person, they don't know that. On their own, these things do not link up because they're going to get a different secret sharing every time. And these websites cannot decrypt any of the secret shares. So we don't break our intended privacy threat model of the web, which is we're trying to make all the apps and websites unlinkable. So if we go back to AdLand here for a second, the app or website that's selling ad space, what does their view look like? Well, they know that they showed an ad impression or got an ad click at some time for somebody. They don't know who this person is. They don't have their identity. They just have some encrypted match key that's pretty much useless to them since they can't decrypt it. Okay, and the website or app that's buying stuff, the one who's selling stuff and buying ads to promote themselves, what do they see? Well, they see something like, okay, someone bought a thing at this time, and I don't know who they are, but I have this encrypted match key. And again, even if these 2 apps and websites cooperate with one another and share data with one another, it's still unlinkable. So even if these 2 rows correspond to the same person, they don't know that. Okay, so this isn't very useful yet on its own, but what they can do is they can at least sort all the rows by timestamp. So I'll go from the most recent to the least recent thing. Okay. And then we can throw away that timestamp column. We don't need it anymore. We just had to get them in order. Next, we can take this, was it a purchase or was it an ad impression column, and just turn that into 1s and 0s, where 1 means purchase or conversion event, and 0 means an ad impression. But you might not want to send this information to the helper nodes, because the number of 1s is like the number of purchases on your website. And that's confidential business information that you might not want the helper nodes knowing. Not a problem. We can secret share it. You can come up with 3 secret sharings, which added together give you either a 1 or a 0. And then each helper never learns the number of conversions on your website. Okay, now what do we do with this encrypted match key? So when you send this information to the helper nodes, each party can only decrypt 1 of the 3 pieces. So helper party 1 has the private key to decrypt this green bit and can get this number. Helper party 2 has the yellow encryption key, and then helper party 3 here has this blue encryption key. So they each get access to just 1 of the secret shares. Okay, that's not enough for them to learn any private information. And if we really want a replicated secret sharing, that's fine. We can have each party just go around in a circle and give its share to the next one around. Now they've all got 2 pieces. Not a problem, still no one learns anything. But we can do all of our fancy additions and multiplications. So what do we have at this point? Well, from helper 1's perspective, it's got a bunch of secret shares, and it doesn't know what any of these numbers are. It doesn't know what these match keys are, and it doesn't even know if each row corresponds to a purchase or an ad impression. But if you had like an omniscient perspective, like if you were all seeing and you had the information of everything inside of all of the three helpers, which no one has this information, but theoretically, it's going to be easier for me in the next few slides to assume an omniscient perspective. Then what you would see is these are secret sharings of numbers that are these match keys. And these are secret sharings of either ones or zeros. So as it turns out, this is all the information that we need to do attribution. First thing that we're going to do is run an MPC protocol to sort the rows by the match key. And I don't have time in my 25-minute slot to explain how to do a sort in MPC, but you're going to have to trust me that it is possible. There's a whole bunch of great academic papers out there getting better and better times on sorting an MPC over time. So what we are proposing using is what's called a stable sort. So a stable sort, if you got two rows that have the same match key, if they were previously in this order before, they're going to remain in that order afterwards. So since we first ordered it by timestamp and then ordered it by this, that means that all the rows corresponding to one person will still be in time order. That's great. Next, we're going to do another MPC protocol I don't have time to explain that compares the match key in each row to the match key in the row above it and produces a secret sharing of a 1 if the two rows are equal and a secret sharing of a 0 if they're not. So in this case, these two rows have the same match key. And so this green row here has a secret sharing of a 1. Okay, now we can throw away the match key. We don't need it anymore. We actually just need to know if each row is the same person as the row above. So in general, attribution, you want to know if there was a purchase that was preceded in time by an ad impression from the same person. Well, we already have that information. This right here, these two rows correspond to an attributed conversion. This row is a purchase. This one came before it in time, and it was an ad impression, and they came from the same person. You can tell that because this row is a 1, that means purchase. This row is a 0, that means ad impression. And this cell here is a 1, which means that they were from the same person. So whenever you have a situation like this, you want to add 1 to the total count of the number of attributed conversions. Okay, well, we can do this with math. We're just going to take this number times 1 minus that number times that number. And in this situation, that gives you 1. In any other situation, it gives you 0. So what we're going to do is we're going to take every single pair of two adjacent rows and do a couple multiplications, and the helpers wind up with either a secret sharing of a 0 or a 1. Then they can just zoom down, add up all those shares, and wind up with a secret sharing of some total, and they don't know what that total is. Now, again, this has been the omniscient perspective. From helper 1's perspective, it just looks like a bunch of gobbledygook. It just knows it's doing some multiplication protocol and winding up with some secret sharing of either a 1 or a 0, and it doesn't know what it is. And then it winds up with some secret sharing of some total, and it doesn't know what that total is. Okay, that's like a very basic level pass over IPA. But one question that's probably on your mind is, who runs the helper servers? Okay, well, we opened an issue on the PATCG's private measurement repo to ask this question, and a bunch of people volunteered, like Tim from ISRG or Cloudflare and other CDM providers. Other people have also volunteered. But the big question is, who decides? Who decides? Who do we trust enough to go run this important piece of infrastructure? Well, it's all about trust. So as a user, you make the decision of what web browser or mobile operating system you trust. So let's say I trust Firefox to take care of my data and keep it private. Well, Firefox can also determine who did they trust to operate helper nodes. And then those would be the only options available. And furthermore, they're going to have to pick groupings of 3 that they think are acceptable groupings of 3. Like maybe you have Bar and Baz here are both running on Amazon AWS. And so hypothetically, however unlikely, if Amazon was to attack its own infrastructure, it could get private information from 2 helpers. And that's not okay. So Bar and Baz might be fine on their own and be okay to appear in other groupings, but they can't be together. So ultimately, as a business, there's going to be some set of acceptable helper party networks for you to choose from. And since you're the one who's going to be paying for these queries, I want to have a couple of options to promote competition and drive down prices. Yeah, and so that would be the one function argument to this get encrypted match key is which helper party network do you want to work with? Okay, there's a lot more to IPA that I don't have time to talk about. Here's a short list of topics I didn't cover, but the good news is you can read more about it. So if you go to the PATCG individual drafts repo, there's an IPA folder, and you can read our IPA end-to-end protocol. It goes into a great deal of detail about a whole bunch of topics on IPA. Thanks for having me here, and it's been a real pleasure to speak to you.
Okay.